Here we have our pre-lab video. In this lab, you are going to be conducting an experiment where your little model airplane is going to fly around in a circle when it's hung from the ceiling. And what we're trying to solve for in this lab is the velocity of the airplane itself. So your setup is going to look very similar to the graphic that we have in our video right now. Since we have the plane, we're going to know what its weight is. We can also measure the length of this string in order to determine other aspects of the lab. Past that, that's all you get. No stopwatch or anything else. So what we have to do is we have to look at our free body diagram in order to draw out our needed force equations to solve this lab. As we can see here in the y-plane, we have the weight of the object that's going straight down, and a true free body diagram would only have tension drawn as our only other force. And when we break the tension into its components, we get the force of tension in the y and the force of tension in the x. For our purposes in this lab, the force of tension in the x is equal to the centripetal force. For free body diagrams, you never draw centripetal force there. But whatever the inward force is, the force that continues to move it in a circular path, is going to be the centripetal force. So here, centripetal force is equal to that component of tension in the x-plane. And also, F sub t in the y is equal to the force of gravity. Since they balance each other out, those are the only two acting forces. So now what we want to do is we want to redraw the triangle that we have. So here, this is the force of tension in the y, and this is the force of tension in the x. And we already said this is equal to mv squared over r, and this is just equal to gravity, which is mg. So if here is our rope, through your own decision and however you draw up your lab, you are going to have to solve for theta. But once you have this angle, what we're going to look at is tangent. Because I have an angle, I have an opposite and an adjacent component. So the tangent of theta is equal to opposite divided by the adjacent. So when we insert the values that we know that we have, these two values, our new formula is going to take shape in mg tangent theta. So I just took the adjacent component, which was mg, and moved it over here, is equal to the opposite, which is mv squared over r. So we insert our known values for f sub t and y, f sub g. This is what our equation is going to look like. Well, what happens to the mass of the object that's moving in a circular path? Look at that. Divides out. So if I'm looking to solve for v, I'm going to get this r moving over here to this side. So v equals rg tangent of theta, and it would be v squared. So if I take the square root of both sides, there I have my equation. And if you think about it, how it's moving around when the object is traveling in its circular path, if it has a small r, so little r is equal to a small velocity. But here, if the velocity is really large, and it creates a large circular path that it goes on, so if I have a bigger radius, is going to equal a larger velocity. So as r gets bigger, the velocity will get bigger. And that makes sense when we swirl things around and we see what they do. All right, so that's all the information you need from me on this lab. Good luck.